Satisfiability of equality equations. This is my favorite question. Just from a submission log, you can tell it's my favorite question already. Anyway, the input is an array of strings and output is a boolean. Each string represents a relationship between two variables. For example, the first variable is A, the second variable is B. This means A equals to B. Now the second string represents another relationship. In this case, it's B not equals to A. Because this is self-contradictory, so we output false. In this case, A equals to B, A equals to B, so it's true. The relationship is associative, so if A equals to B, B equals to C, A equals to C, that is also correct. A equals to B, B not equals to C, C equals to 0, that is self-contradictory. C equals to C, B equals to D, X not equals to Z, so that is fine as well. The length of each string must be 4, and the first character and the last character are always lowercase characters, and the second character is either equal or not equal sign, and the third character or index 2 is always the equal sign. The second variable is not necessarily different, meaning it's possible you have A equals to A as a string, or A not equals to A as a string, which we know is false straight away. So pause the video and see if you can solve it. Let's check out this test case. A equals to B, C equals to B, D equals to E, E equals to F. So far so good, because ABC is one chunk, DEF is one chunk. They have nothing to do with each other. Then F equals to A, we are connecting these two chunks, right? So ABC, DEF is one chunk now. Then G is not equals to C. This is not a problem. So G is its own chunk, C is its own chunk. Then D equals to G, well, that introduces a problem because A all the way to F is one chunk, and G previously says it's not part of the same chunk, but now you say you are, so it's supposed to be false. What is the intuition for this problem? When I say they are the same chunk, you can also think of they're the same clique, they are the same club, same exclusive club, or the same set. The algorithm is called disjoint set or union find. As long as a variable is a part of a clique or set, it cannot be a member of another club at the same time. For example, A equals to B, they are the same club. C equals to B, they are the same club. D equals to E, they may or may not be the same club. We don't know. E equals to F, they are the same club. F equals to A, and here we have a connection, right? So we are the same club now. Everybody is the same club. Because of F equals to A, then G is not equals to C, so we know for a fact that they must not be the same club. Then if you say D equals to G, all of a sudden you are self-contradicting, so it's false. So how do we know if some variables are part of the same set or a different set? What union find algorithm does is that we set a parent for every variable. There are different ways to set parent. To keep it simple, I'm just going to make the first variable a parent. There are ways to optimize this, for example, compression find. But to keep it simple, I'm not going to do that. I'm just going to make the first variable the parent. So B's parent is A, P means parent. In a graphical representation, it just means B's parent is A. A's parent is itself. Originally, everybody's parent is itself, so we just say everybody's parent is itself. Then we say B's parent is C. Okay, previously B's parent is A, so we go to A and say your parent is C now. So we change to C and also change B to C. So graphically, B's parent should be C and A's parent is also changed to C. Then E's parent is D. E's parent previously is itself, so now it's D. So E's parent is D. F's parent is E. F's parent is E. Who is E's parent is D, right? So F's parent is D. F's parent is D. Then A's parent is F. Who is A's parent is C. So we go to C and we say C's parent is F. But who is F's parent? F's parent is D. Who is D's parent is itself. So ultimately, we are actually saying that A's parent is D and C's parent is D. So we are migrating A and C to D, right? Let me clean it up. Now B's parent is never changed because we didn't visit B, right? Because previously, when we are setting A's parent, we are visiting C. We visit C. C's parent previously was C. Then we set to F's parent, which is D. D's parent is D, right? We never visit B, so B is still here. Then we say C's parent is not G. This may potentially be a problem, but let's just see what it does. C's parent is D, right? D's parent is still D. So D parent is not G. For now, there's no problem because D is his own parent and G is his own parent. Okay, looks like there's nothing to do. But then we say G's parent is D. Who's G's parent is itself? Who is D's parent is itself? So you see what the problem is. Previously, when we say C's parent is not G, we are actually saying D's parent is not G. But now D equals to G, we are actually saying G's parent is D. So there is a contradiction here. But we do not know this contradiction because previously at G not equals to C, we didn't do anything. It didn't leave any mark. So instead of doing in this sequence, why don't we do all the equality first and then move the inequality to the back? In the code, we can just do two loops, right? So we do D equals to G first, right? So G's parent is D. So we set G's parent equals to D. So in the graph, we say G's parent is D. Then C's parent is not G. Who is C's parent is D, right? D's parent is still D. Who is G's parent is D. So you cannot say C's parent is not G because, you know, C's parent is D, G's parent is also D, D is the same as D, right? So it returns false. So what should the code look like? I'm going to use an array of length 26 to represent all the characters because the input variables are all lowercase. You can also use a hash map to do this, but I'm going to use an array. You can make the case that it makes the code cleaner. Well, you can also say that array is a continuous blob of memory. So if you iterate through, because of locality, it will loop through faster instead of a hash map. So you're jumping in memory all over the place. But again, since the length is 26, so it's trivial. I'm just going to say UF equals to array 26 dot fill dot map I think this works. Let's console log it and see if it makes sense. From 0 to 25, yes, okay. So lowercase a is represented at the zeros index, and lowercase z is represented as the 25th index. And initially, the value and the index is the same. So whenever you see value and index is the same, you know that variable is its own parent, right? So initially, there are 26 different sets. So now we will loop through the input array of strings. We will do it twice because the first time we're going to do equality, the second time we're going to do inequality. So if E1 is equality sign, right? Then later we do if E1 is inequality sign. And inside this equality sign, we're trying to union the first character and the last character, right? So what is the first character? First character is E0 dot char code at -27. Why is it 27? Because in ASCII table, lowercase a is 97 in decimal. And the last character is char code at -27. And we want to make first character be the parent of the last character. But not only make first character be the parent of last character, strictly speaking, is make F's parent be the parent of L's parent. Let us walk through an example. So in index form, the character or string doesn't exist anymore. We are using number index to represent that character. So initially, the index and value matches. This represents A is its own parent. So walk through from the beginning. B's parent should be A now, so 0. B's parent should be C now. So B changed to C, A also changed to C, E changed to D, E changed to D, F changed to E. So let's look at A changed to F, which correspond to my comment here, which is make F's parent be parent of L's parent. Kind of a complicated sentence, but basically it's saying we go find A's parent, right? A's parent should be go to index 2. Okay, make C's parent F's parent. What is F's parent? Go to index 3, which is D. So you are overriding value 3 here. Now this find parent method is actually a depth first search technique. You can think of it as trying to seeking for root, right? As long as the value and the index doesn't match, that means the root is somewhere else. So we are going to assume we have that method. We're going to write it later. So parents, let's use find. We're going to write find later equals to find first, making the first character's parent, but you need to first find it, right? So we say find the first character's parent and make it be the parent of L's parent. So this is L, you need to find F's parent. Okay, so let us write the helper function, which is find, and take in a, let's say E. This is a depth first search method. As long as the value and the index does not match, we need to keep seeking. And so you can do parents E equals to find parents E. If the index and the value doesn't match, you need to go to the parents and go find it. Then you assign it. Then you return parents E. But I just realized this is actually 3, not 0. Okay. Then we go to the inequality. We can reuse the constant. I just want to mention that I changed the for each to a for loop because in this function I want to early return. If you use for each, the early return will not work because for each has its own callback function. If you return inside here, it will only exit out of the for each. If I use for each, it will not return the whole function, but inside this I want to exit the whole function. That's why I changed to a standard for loop. If find first is not equal to, no, if it is equal to find last, we return false. And in the end, we return true. If it works, moment of truth. It works. So there we go. Now, what is the time complexity for this find function? It looks like recursion, so is it very costly? Well, if you go to here, the find operation is actually amortized all of 1, and we're doing 2 passes, so each pass is all of n, so overall is all of n. Although there's some disagreement over here, but personally I believe the find function is amortized constant, because I am always reassigning the value in, well, he called it UF, I call it parents. I'm always reassigning it to the top level parent, right? So the first time it may be costly to find it, but the second time if you find it, it's always all of 1. I'll leave a link to another video explaining time complexity for union find. Hopefully you can find that useful as well.